Hello and welcome to Lecture 16 on the topic of electromagnetic waves. This is the final lecture in our 16 lecture sequence on electromagnetism, building up from the definition of charge and finally finishing here. I made a big deal in the last lecture, in lecture 15, how RLC circuits were the culmination of many ideas about circuits and electromagnetism in general, and that was absolutely true. But electromagnetism and talking about EM waves is not only truly the culmination, but is also a segue to content to come. Because in the very next lecture, in lecture 17, we're going to be talking about optics. And optics is all about considering what light does as it bends and spreads and all the interesting phenomenons that we can discuss with light. Okay, well, let's talk about electromagnetic waves and photons. Our first objective is to learn insight into how electromagnetic waves were theorized by Maxwell's laws. Then we want to see how to calculate the speed of light and the energy of individual photons. We want to understand the concept of light intensity and the momentum possessed by light. We want to become acquainted with the electromagnetic spectrum and the temperature-dependent spectrum of solid objects as described by Wien's law. And finally, we want to learn that polarization of light is one of the consequences of light being a wave. Okay, now really, we're going to talk a lot more about light in lectures to come. Okay, so what is an electromagnetic wave? Well, it's light. Okay, light is an EM wave is light. Okay, no exceptions. It is a self-propagating wave created by the mutual inductance of electric and magnetic fields, the E and B fields. Okay, because we know that a changing magnetic field induces a changing electric field and vice versa. EM waves are created anytime a charge is accelerated because we know that a constant current, which would be a constant velocity charge, at least idealized as such, creates a steady magnetic field. And the steady magnetic field created by a constant current cannot induce a current. We need a changing magnetic field. Thus, it's only the acceleration of charges that creates light. If you move a charge at constant velocity, light will not be created. But if you accelerate that charge, either by taking a charge like an electron and making it take a curved path, or slow down or speed up, and invariably light is created. That is one of the biggest takeaways, the biggest ideas in all of electromagnetism, that light is created by accelerated charges. Here is a visualization of light as an EM wave with a perpendicular component of an electric field that is varying and a magnetic field that is also varying with that self-induction, okay? So what are Maxwell's laws? Well, they are the governing laws of all electromagnetism, which also means they're governing laws of circuits and the governing laws of, soon to come, optics, talking about the bending and spreading of light and such, okay? Maxwell's laws are a collection and refinement of Gauss's, Ampere's, and Faraday's laws. That's what it represents, the culmination of all the ideas we've talked about. And only Maxwell's laws make it clear that the EM wave is light and is created by the acceleration of charges. Okay? All right, on to polarization. Well, polarization is the selecting light selecting light with a vector, an electric field vector, or a magnetic field vector in only one direction, only a certain direction. All right, so instead of having multi-directions, just having a single direction of an E field or a B field. In fact, when we draw EM wave to show these perpendicular components of the E and B parts of the wave, we are essentially drawing polarized light because we're only showing the electric field in one direction along this particular axis here. We could say that's the y-axis. All right, that's an example of polarized light. Unpolarized light, on the other hand, has electric field vectors and magnetic field vectors in all directions. And that's called unpolarized light. And it's the most common type of light that's produced because most sources of light create unpolarized light. It's only through lenses that we can polarize that light. Okay, so on to the photon. Well, the photon is a particle of light, but light's a wave, right? Well, light has energy proportional to frequency of the electromagnetic wave. So obviously the particle and the wave are connected. In fact, Light is both a wave and a particle. That's called the duality of light. Now, there's a lot of ideas here that we're just touching on that we're going to return to after optics when we get into what's called modern physics, where we talk about quantum mechanics, which that talks about the photon. And when we talk about special relativity, we'll talk about the speed of light and the idea that the photon has momentum, which we'll see on the next page in our key equations. Okay, so moving on to the electromagnetic spectrum. Well, it is an expression for all forms of light from radio waves to gamma waves. So we see here that we have gamma rays at the top and radio waves at the bottom. This is the spectrum. All right, one very small part of the spectrum, this dark blue section, which is expanded over here, is the visible light part of the electromagnetic spectrum. Just outside of visible light, with a slightly shorter wavelength, is ultraviolet light, and with a slightly longer wavelength is infrared rays. Because we see that the wavelength, measured here in centimeters, grows as we go down. On the other hand, the frequency decreases as we go down the electromagnetic spectrum, and the energy per photon also decreases as we go down the spectrum. Notice also that the energy per photon is expressed in electron volts. Okay, so that's the entire spectrum, that's all of light. Unlike other waves, light has a fixed speed, so the frequency, wavelength, and photon energy are all determined by each other. So if you know one, you know all three. Okay? Wien's law, our last idea here, is an experimental law that states that the wavelength of light emitted by solid objects is inversely proportional to the temperature of the object. Now, that idea of solid objects emitting light is actually part and parcel of the very history of quantum mechanics that led to the photon. And later when we talk about that, we will talk about the idea of black body radiation, which ultimately leads to this empirical law, this fitting law, a function that fits the observed behavior called Wien's law. So again, this idea that there's so many ideas here in this lecture that will be expanded upon much later on. Additionally, the idea that we're talking about wavelengths of light, of course, is so important to the atomic understanding of how atoms can absorb light and emit light of particular frequencies, and even the Bohr model of the atom. So many ideas, but much to come. One more thing about Wien's law is that all objects emit light because the molecules vibrate and result in the acceleration of electrons. Because as I said a moment ago, anytime a charged particle accelerates, light is created. Well, every molecule has atoms inside which have electrons. If that molecule is jiggling back and forth, that means it must be stopping and starting. That means the electrons are along for the ride and they must be accelerating. Any start and stopping motion is acceleration. Thus, EM waves must be emitted. Now, most objects don't emit light in the visible spectrum. So we don't see them glowing. Instead, we see them reflecting light from the sun or from another light source, like something that is glowing hot enough to be in the visible spectrum. But everything emits light, okay? All right. So moving on to the key equations. So our first one is the speed of light, represented by the letter C. And the speed of light is actually equal to 1 over the square root of two of the biggest constants that we've seen throughout the last 16 lectures, the permeability constant and the permittivity constant, really showing how all these ideas are connected, which of course is justified by Maxwell's laws. All right, and it is also equal to the instantaneous value of the electric field. All right, so that would be the magnitude of the electric field vector and the magnitude of the magnetic field vector. And that ratio is equal to the speed of light. So in other words, if you know the electric field strength, then you automatically know the magnetic field strength of that EM wave because C is a constant. It is invariable. All right? And how do we know that C is a constant? Well, that takes us to Einstein's special relativity. We'll get there later. The actual value of the speed of light is 2.998 times 10 to the 8 meters per second, or about 300 million meters per second. Okay? Furthermore, we have the idea of intensity. Intensity is almost a new way to talk about energy, because we've talked about energy, storing energy, possessing energy. We've also talked about energy per time, which is power measured in watts. But if you have power per area, so that's like light energy spreading out over an area, well, now you have something called intensity. So it's power per area, watts per square meter. okay? It can be expressed in terms of the magnitudes of the different components of the EM wave, the electric and magnetic components, as well as the permeability constant, or we can express it in terms of just the electric part and the speed of light, or just the magnetic part and the speed of light, okay? So a number of ways expressing the intensity of light of known field strengths, okay? Furthermore, we can relate the intensity of light to the energy that that light can transmit, because intensity times area multiplied by time, of course, gives you energy. That would be the energy collected by a solar panel, for example, or the energy that is going into a body of water and heating it up from sunlight, all right? You just need to know the intensity of light, how big the surface area is, and how long that surface area is exposed to the light, all right? So A for area, and then delta T for elapsed time. And furthermore, we can express the intensity from a single source, like a point source, right? So some source of light. Well, that intensity spreads out into spherical shells that become larger as the radius becomes larger. So it's helpful to think of intensity as power divided by the surface area of a sphere, because certainly in space, light spreads out in all dimensions freely as a imaginary spherical shell of energy. Okay, moving at 300 million meters per second. Okay, next we're going to talk about the speed of light and its relationship to wavelength and frequency. All right, and this is just a testament to the fact that if you do know the wavelength of a particular source of light, then you can find the frequency by just dividing the speed of light by that wavelength, or you can find the wavelength that way. Okay, all right, now on to the energy of an individual photon. So this is E sub photon, that's energy per photon. It's equal to HF. Well, what is H? H is something called Planck's constant. It is one of the fundamental constants of the universe. In fact, there are really, as far as we know, only 3 fundamental constants of the universe. And at this point in physics, you have now seen all 3 with the introduction of Planck's constant. Although you might have seen Planck's constant earlier on in the discussion of thermodynamics. But here we see Planck's constant, which is equal to 6.63 times 10 to the negative 34. It has units of angular momentum, which is joule seconds, very much connected to the history of quantum mechanics, as I mentioned, and certainly we'll talk about later. And it holds a place with other constants of the speed of light, okay, another constant in the universe, and last, the gravitational constant. Those 3 experimentally determined constants seem to almost be the tuning values of our very universe. Okay, now on to Wien's law. So here is Wien's law, right? Empirically collected. Here it is as an equation, and here is a graphical representation of Wien's law. The idea is that there is a peak wavelength emitted by solid objects that have a surface temperature of T. So hotter objects have shorter wavelengths because it is an inverse relationship. So we can see an object that has a surface temperature of 7,000 Kelvin, which would be like a hot star, has a peak wavelength in the visible spectrum right around blue light. Furthermore, if we have an object like the surface of our own sun, which is somewhere between 6,000 and 5,000 degrees Kelvin, or Kelvin, then it's going to have a peak wavelength in the range of somewhere between, well, I look at the 6,000 curve, it has a peak in sort of the light or the bluish green color, and then the 5,000 curve has a peak right over in the orange. So it's often stated that the peak wavelength of our sun is right in green. Does that mean our sun appears green? No, it just means it has a peak wavelength. The most probable wavelength of light that is created from the surface of the sun is a photon that corresponds to green light. But it also means that there's a lot of blue and orange and red light and such that's also created. And so the overall effect is the superposition of all those colors, which appears white. Okay? So that's Wien's law. And certainly as we get into cooler things that are, say room temperature, obviously, at 300 Kelvin, then the peak is going to be well outside of the visible spectrum in the infrared, IR. Okay, now let's talk about the momentum of light. So here's light energy, just like the expression used up above for light energy when we relate it to intensity. Now, if you're wondering why we're using U for light energy, that's to make it clear that we're not using the same letter E for both the electric field and energy. So we're using U for energy. And P here represents the momentum. This would be the imparted momentum from absorbed light. Because although we don't notice that light pushes on things because the force and the momentum is very small, light does push. Light can be used to hold very small things like tiny beads used in certain molecular processes and in science. It also can be pushed on if you have a very large area and a very light object, and there is a discernible amount of push from light. It's relevant in the tails of comets. The tails of comets get pushed by the momentum of the photons coming from the sun. But the point being is that light does have momentum. Now that is quite interesting because we will show later that light does not have mass, but yet it still has momentum, which takes us right back to modern physics and the special theory of relativity, okay? But not our topic today, I know. We're just talking about the momentum of light as it directly relates to intensity and the speed. Now, we can also talk about the momentum when light is reflected, and it's just twice as much as when it is absorbed, which certainly makes sense in the context of conservation of momentum, because if a photon bounces off something, then it has a change in velocity that is twice as big than if that photon was just absorbed, okay? All right, and finally, on to the equation that's relevant to polarizers. First, over here, I have a picture that shows a polarizer. This is the unpolarized light I mentioned a minute ago that has electric fields pointing in all directions. And these vectors here could represent the electric field, and usually do, but they could just as well represent the magnetic field. But the point is that those field vectors are pointing in all directions. They are equally distributed. When they pass through a polarizer, a special type of lens, only one direction survives. That's the idea of polarization. Okay, and if you have two polarizers that are perpendicular to each other, then these ones are vertical and these ones are horizontal, and you can kind of think of the polarizers as many closely placed slats, then no light passes through because the angle between them is 90 degrees. And indeed, the equation supports that because if we plug in 90 degrees into our cosine function, we get 0, which tells us that our transmitted light is 0. And I here is intensity. All right, this is called Malice's law. All right, and again, it is only really dependent on the incident intensity, that's the watts per square meter, the transmitted intensity, the watt also measured in watts per square meter, which is the result of the effect, and the angle between the two, okay? Here's an example of that angle between the two polarizers, okay? All right. Moving on to our practice problems. Pretty straightforward problems. Obviously, the focus here is mostly on the conceptual ideas. Type 1, problems that involve making calculations of field strength, intensity, and energy in light sources. Type 2, simple problems that involve the electromagnetic spectrum and relating wavelength, frequency, and photon energy, which may include solid object sources of light of a particular temperature. Type 3, simple problems that involve the momentum carried by light and the conservation of the momentum during reflection and absorption of light, so using those two formulas with momentum in them. Type 4, problems that involve the polarization of light and the intensity of transmitted light through two or more polarizers, okay? All right, example 1, a radio antenna broadcasts a 1 megahertz radio wave with 25 kilowatts of power. Assume that the radiation is emitted uniformly in all directions, so it's that spreading sphere of energy. What is the wave's intensity 30 kilometers from the antenna, from the source, okay? All right, so how would we go about doing this? Well, we want to go ahead and consider our frequency here. All right, so this is just converting it over into the correct units, right, base units. And here we have the power in watts. All right, so this is going to be our formula to relate intensity, power, and our area of our spreading sphere of energy. And we just plug in our values, including our radius of 30 kilometers, and we end up having an intensity, which is very small, of 2.21 times 10 to the negative 6 watts per square meter. But that makes sense because radio waves are not terribly powerful to begin with, okay? All right, now in part B, what is the electric field amplitude at this distance? Okay, so now that we know the intensity, we can go ahead and find the maximum value of electric field, which is its amplitude, just by isolating that expression for the electric field, plugging in our values, including the answer that we solved for in part A, and getting our answer of 4.08 times 10 to the negative 2 volts per meter, Okay, all right, well, on to a concept question. Now, this concept question doesn't have much to it. It's just the idea that the electric field is perpendicular to the magnetic field, but it's a pretty picture. It's like the one on the front page. The electric field for a plane, that means planar, electromagnetic wave, traveling in the y direction is shown. Consider a point where the electric field is in the positive z direction. The B field is in what direction? Well, it's got to be perpendicular, which means it's got to be in the x direction, right? So the magnetic field is entirely in the xy plane, just like the electric field is entirely in the zy plane, okay? All right. Example 2. Determine the amount of energy carried in 2 meters of a 4.6 milliwatt helium neon laser beam if the cross-sectional area of that beam is 4 times 10 to the negative 6 square meters, okay? So the idea is we actually have a volume of energy here. So we have intensity, area, and elapsed time. Now the elapsed time is just going to be distance times velocity, because then we can find out how much, how much overall energy it took to carry along those 2 meters. So we have our 2 meters, we have our speed of light at about 300 millimeters per second. So we have that the light only takes 6.67 nanoseconds to travel that far. This is a testament to how fast light is. All right, so now we can go ahead and use that time along with our power and area and our distance in order to find the actual amount of energy in that beam. All right, so again, it's a volume of light that we're finding the energy in. All right, so we plug in our values and we find out that that laser beam contains 2.5 times 10 to the negative 8 joules. All right. Okay, so taking a look at example 3. Okay, so a solar cell has a light gathering area of 12.4 square centimeters and produces 0.4 amps at 0.93 volts. Okay, it's DC. All right, when illuminated with sunlight of intensity 884 watts per square meter, which is pretty realistic of the type of intensity light there is on the surface of Earth. What is the efficiency of the solar cell? Well, the power output of the cell is simply found from this familiar equation for circuits, which is just volts times current. Okay, and we were given the current and the volts, so we can easily find the power output of the solar cell. Okay, well, what about the power input? Well, the power input is intensity times A. Notice here I actually wrote the word intensity. That's because otherwise I would have had I representing both current and intensity, all right? But anyway, so here we have intensity times the surface area, okay? So then the efficiency is just going to be the power out over the power in. So we just have our volts times our current divided by our intensity times our area. Notice I converted the square centimeters to square meters, and we get a efficiency of 0.416 or 41.6%, okay? All right, let's do a problem with Wien's law. The surface temperature of the sun is 5,778 Kelvin. Well, okay, so if that's the temperature, and the value in Wien's law in the numerator is just a constant, then we can easily find the wavelength, which we're asked for in part A. What is the peak wavelength? Okay, well, this is the formula for the peak wavelength. So we get 502 nanometers within the visible spectrum. Well, that makes sense because we have evolved to see the light from the sun. Very well. All right, let's go ahead and find the frequency of that light. Well, then we just take the speed of light divided by that wavelength. And so that means we take something very fast, a velocity that's very fast, c for the speed of light, divided by a length that is very, very short. So we get an incredibly high frequency, right? It is in the hundreds of trillions, okay? 5.98 times 10 to the 15 hertz. That is how quick the wave of visible light oscillates up and down. It's incredibly fast. It's why maybe we can't create visible light with antennas. It's good luck getting an electron to oscillate up and down that quickly. It would violate the special theory of relativity because it couldn't go that fast. Furthermore, it just goes to show how quick that oscillation is for visible light. And it's actually quite interesting because the actual wavelength of visible light is not that small, right? There are plenty of things that are smaller than visible light. That's why we have to use electron microscopes to observe small features on, say, pollen grains and insects and such. So light itself is not very short, but it certainly oscillates very quickly. And finally, in part C, okay, based on the power output of the sun, how many photons are released by the sun each second? So our power output of the sun is 3.8 times 10 to the 26 watts. All right, so a lot of energy coming from the sun. So the number of photons is just going to be the power divided by the energy per photon, which is Planck's constant times the frequency. All right, so there we have it, right? So total power divided by energy per photon, and we end up with 9.59 times 10 to the 44 photons per second. Unbelievable amount of photons being created by the sun every single second. Now, of course, that's fascinating for so many reasons because the sun is producing those photons through fusion, which means that there's actually matter becoming pure energy at a fundamental scale. So you just think about the sheer amount of matter that is just disappearing as this much energy is being created in the form of photons. And furthermore, it's just such a staggeringly large number, but it's really, if you think that photons are one of the smallest fundamental particles there are, then I suppose it makes sense that there's just so many of them. Okay, all right, well, let's talk about the idea of light's momentum in a solar sail example. So a solar sail is an actual type of spacecraft that has not been applied too much, but maybe will be more common in the future, of having a very large surface area, kind of like an array of solar panels that are made out of very light material attached to a small space probe. And then the space probe doesn't use any traditional type of propulsion in terms of rocket fuel or anything like that, but instead will propel itself from the momentum that is being imparted to the solar sails from the sunlight of the sun. Okay, so here we have a 100 kilogram spacecraft, so a rather massive one. considering that it's based on a solar sail model that has a surface area of the sails of 3 times 10 to the 4 square meters. So huge, massive sails are meant to unfurl as they go out into space. They are absorbing sunlight, and the sunlight has an intensity of 700 watts per square meter. Okay, so they're somewhere out beyond Earth's orbit where the sunlight is slightly less intense than it is here. What is the resulting acceleration of the spacecraft? So how do we go about doing that? Well, we'll take our momentum related to energy divided by the speed. We're going to then change the momentum here to intensity, area, and elapsed time. And then we'll note that the momentum divided by that elapsed time is force. So we never actually solve for the elapsed time, nor do we need it, because we're interested in the force. And then we'll relate the force by Newton's second law to the mass of the spacecraft times its acceleration, which we were asked for. That means that the acceleration is the intensity times the surface area of the sail divided by the speed of light and the distance. Okay? All right, oh, and the mass, excuse me. Because of course it's acceleration, okay? So then our acceleration, then we plug in all our values because these are all known quantities, and we find out that our acceleration is 8.01 times 10 to the negative 4 meters per second squared. So very, very slow acceleration, but without any drag in space, after a while, it would pick up some speed. It would just be very slow at first, but then after it starts moving quickly, it would then obviously continue to do so, right? Because there's nothing to slow it down. All right, what if instead, in part B, if the sail is reflective? Well, that's better because now we should get twice as much momentum, right? Because we're going to have, the momentum of reflection rather than absorption, which means that our acceleration is just twice as large, or 1.6 times 10 to the negative 3 instead, meters per second squared. Okay, all right, let's do our final example, one with polarizers. 3 polarizing sheets are placed in a stack with the polarizing directions of the first and third perpendicular to each other, all right, which would allow no light between them if it was just the first and the third. What is the intensity of the light emerging from the third polarizer if the middle, there's the middle one, has a polarizing direction that is 70 degrees to the first, okay? And take the initial light as unpolarized with an intensity of 1,000 watts per square meter. So here's the picture, right? Here's our initial unpolarized light with electric fields pointing in every direction, right? That's our I naught for intensity, okay? Our first polarizer we'll draw it as a horizontal, and our last one is as perpendicular. And again, if we just had the first and the third, no light would be transmitted because it would be cosine of 90 degrees, right? It would be zero. We'd be blocking all the light, which makes sense because only the horizontal component would survive the first polarizer, then the horizontal component would hit up against the second polarizer that only allows the vertical component through. But the amazing thing about polarizers is if you put a third one in between that is angled relative to both, now light passes. Because this middle one, since it's angled, will create both horizontal and vertical components, and some of that vertical component thus can survive the third polarizer. Our angles are 70 degrees, that's the angle between the first and the second, and since we know that the third must be vertical, the angle between the second and the third is 20 degrees, okay? And I call those phi alpha and phi beta. All right, so we're going to use the polarizer analyzer equation, also known as Malice's law, all right, where phi is the angle between the polarization axle and the intensity is the output from the next polarizer, okay? So what I mean by that is we're interested in the final intensity, all right, I3, but I3 is dependent on I2, okay? Well, then we can replace I2 with a repeat of Malice's law, all right? So I've just replaced I2 with I1 times cosine of phi alpha. So now we have a initial intensity, I1, that's intensity coming out of the first polarizer, times cosine squared of the first angle between the two polarizers times another cosine squared of the angle between the second and third polarizer. Okay, all right, and then I replace I1 with 1/2 I naught because I don't know I1, but I know that I naught is 1,000 watts per square meter, and I know it's 1/2 because anytime you go from unpolarized light to polarized, you lose half the intensity up front. That's a rule of polarizers. From polarizing the original unpolarized light, that's where the 1/2 comes from. No cosine necessary there, you just cut it in half. Okay, so we're good to go now. We can just do our calculation, and we get that it is about 5.2% of the original intensity, all right, if we were to convert this over to percent, or if we just multiply by the actual value of 1,000 watts per square meter, we get that 52 watts per square meter is the intensity of light that comes out of the third polarizer. Quite a bit has been lost, okay? All right, well, that concludes our lecture on introducing EM waves and building a bridge between electricity and magnetism and optics. All right, well, I hope this has been interesting and informative. Thank you so much for watching.